Alright, welcome back to Academic Chem. My name is Mr. Kubuske, and today we're going to be talking about transfers of energy, otherwise known as thermochemistry or calorimetry. All of those are acceptable names, but this has a lot to do with, again, properties of atoms, compounds, and molecules, which is the focus of Unit 2. I know we've been jumping from chapter to chapter to chapter, all part of this. Unit 2 included Chapter 2, part of Chapter 10, and now part of Chapter 17. But trust me, it all kind of goes together. You'll see how it all links here in a second. But I'm going to disappear for a second. I'll come back at the end and we'll work on the board. But let's talk about exactly what thermochemistry is, the transfer of energy. So why does lava cool faster in water than it does in air? Well, now this is logical to you. You could think about it. You would say, oh, well, the water's cooler than the air, so that means it's going to cool down faster. Well, that's true, but when we talk about heating things up or transferring heat, what we're really talking about is energy, because heat is a type of energy. The greater the difference in the heats, then the faster that energy is transferred, or the faster the heat is lost. And heat will continue to transfer until they're balanced on either side. So how do we calculate that number? How could we put a tab on exactly how do we know how much energy has been transferred? Well, we use a fun little saying, which is Q equals MC delta T, MC delta T. Q equals MC delta T, MC delta T. It's a good thing I don't have the camera on right now, because you probably would have been laughing pretty good at me. No, but Q equals MC delta T excuse me, is our formula to calculate the transfer of energy loss. Or gained, I guess, in that case as well. Q equals heat. Heat is the energy that transfers from one object to another because of the temperature difference. Okay. Now you may say, oh, well, I heat up my, macaroni and cheese or whatever in the morning, or I guess at lunchtime. But what you're really doing is you're transferring energy from one source to another, and the one that has the warmer source transfers its heat or its energy into the one that's cooler. If you're talking about a stovetop, then the stovetop itself would be the hotter substance transferring its heat to the cooler, which would be like boiling water or whatever you're heating up at the moment. Heat is measured in two ways. Calories. Calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. So calories are actually pretty easy to use because it's usually just like 1. So that calorie, that amount becomes pretty simple to work with. Joules is the actual SI unit, but if we ever work with joules, I'll give you the number. I would never just leave you without that number. I would give that to you. They're a little bit more difficult, but you can talk more about that later on. So M equals mass, just like always. Mass is the amount of the object that we're going to be actually heating up. So it's the mass of the object will determine how much heat it takes to raise temperature 1 degree Celsius. So obviously if something has more mass, it's going to take more energy to heat up. C is a different one for you. It's a new one. C equals specific heat, and that's the amount of heat that it's required to raise the temperature 1 gram 1 degree Celsius, which is 1 calorie. Okay, but if we're going to use joules for water, it's 4.184. So 4.184 joules of 1 gram 1 degree Celsius. So you'll notice the formula here, the joules or the calories, whichever unit you're going to use, you would not use both. You'd have to make sure you know the difference. Okay, you're either using cals or you're using joules. So you're either using 1 cal or 4.184 joules is always over 1 gram 1 degree Celsius. That'll be important when we go to set up our actual formula. Okay, but again, we're using the specific heat of water, and we'll use that for pretty much all of our examples. And if I would ever use anything else, I would give you the numbers. And then lastly, delta T. You're going to see delta a lot in future science classes. Delta means change or difference. So delta T means change in temperature. And you can calculate that by doing the final temperature, or T final, minus T initial. Some people will call it T2 minus T1. In other words, the temperature the second time you measured it minus the temperature the first time you measured it. Either way you want to describe it is fine, just as long as you know that it's final minus initial and it's the change in temperature. Okay? So how do we actually do this? Well, let's do a problem together. Okay, it says determine the energy transferred when 50 grams of water is heated from 25 degrees Celsius to 35 degrees Celsius. So it gained 10 degrees. How much energy does that actually take to do that? Well, we start with our formula. Q equals MC delta T, MC delta T. Okay, and then what I'm going to do now is I'm going to figure out what I know. What was I given in the problem? Okay, well, do I know Q? Do I know how much energy was transferred? No, that's what I'm trying to find out. Do I know the mass? Yes, it's 50 grams. Do I know the specific heat of water? And again, I'm always going to give that to you as part of the problem. For this one, let's do it in joules. So 4.184 joules over 1 gram 1 degree Celsius. Again, you have to have that all together. And then the change in temperature, we went from 25 to 35, so I flipped those numbers because the T final is 35, the T initial was 25, so it's 35 minus 25. Now I'm going to put those numbers into my little formula here, and I'm going to do that by breaking up, okay, the Q equals MC delta T into this little grid, okay? And the reason I do that is it helps me organize my information. So my Q I don't know, I still have Q equals. My M I do know, it's 50, so I'm going to take this 50 and I'm going to put it right there, 50 grams, okay? And then my C, my specific heat of water, goes here in the middle, 4.184 joules, okay, but that's over 1 gram, 1 degree Celsius. So that goes on the bottom here, okay, 1 gram, 1 degree Celsius, and that's important here, I'll show you why. And then I put the change in temperature, the 10 degrees Celsius, up here in the top where delta T would go. Okay, so I've completely taken that formula, I've put it in this little grid. Now here's the reason I use the grid. I need to eliminate my units that are both on the top and on the bottom. So I have grams here and I have grams here. Let's get rid of them. I have degrees Celsius on the bottom, I have degrees Celsius on the top. Let's get rid of them. So the only unit I'm left with is joules, which works because that's how I figure out the energy transferred. I can get that number from joules. So the J stays. Okay, so Q equals 50 times 4.184 joules times 10. When I do that, I get 2,092 joules. And if we want to use specific sig figs and stuff like that, it'd be 2,100 joules. That's fine. Joules are always going to be large numbers. They're always going to be usually pretty high up there. And it's hard for students to understand the joules number because you have no basis for it. You have no, you can't refer to other things in your life and say, oh, well, I know that that's this many joules, so that makes sense that this would be this many joules. Okay, you just kind of have to trust the number. If the answer is negative, that means energy was released, meaning that something cooled down. If the answer is positive, that means energy was absorbed or something heated up. Okay, so since our number was positive, 2,100 degrees or 2,100 joules, that means we increased 10 degrees. Okay, so how do we calculate temperature change of a specific heat substance? Just like in math, what if we were given Q but we were asked M? What would we do? Well, we would kind of reorganize our formula so that it made sense. Okay, but again, you'll see we're just going to solve first and then we'll rearrange. Okay, so let's say, like in that last problem, okay, I know the 2092. I knew the 50 grams, I knew the 4.184 joules, but I didn't know the change in temperature. Okay, let's just assume we didn't know it. Obviously, we do know what it should be, so let's see how close we are. Okay, again, cross out units. Okay, now I have joules here and I have joules here. Now, technically, that would be the top and the bottom because they're on opposite sides of the formula, so I can cross out the J's. Okay, so I'm left with degrees Celsius. Now, what I do is I rearrange that whole thing in order to get my answer. Let me show you how I do that. Okay, so I start with my 2092, which is my Q on one side of the formula. I have my 207.4, which is what I calculated when I multiply 50 times 4.814. I have that number. I can't do anything with the delta T, so that stays behind. The 1 degree Celsius stays behind as well because I'm not able to get rid of that. Remember, I crossed out the grams here, so I was able to get rid of that 1 because it doesn't really matter because it's 1. Now, I have to rearrange things in order to do this problem. So I take the 207.4, and when I send it to the other side of the formula, it goes on the bottom. I take the 1 degree Celsius, since it was on the bottom, and now goes on the top on the other side. So I multiply 2092 times 1 degree Celsius to get 2092 degrees Celsius, divided by the 207.4. Now remember, there's no unit for that one because we got rid of the unit up here. And that's all equal to delta T. So when I do that, I divide 2092, do that times 1, and then divide by 207.4, and I get 10.09 degrees Celsius, which would round to 10 degrees Celsius, which I know from the previous example. Let me just get it all the way back there. If you can remember right here we said that it was 10. So all I did was I used this number to find that number. Okay? So that's how you rearrange things. Again, you have to find out what you're looking for and then rearrange. If it's on the top, it goes to the bottom. If it's on the bottom, it goes to the top. Cross out units. Simple. Okay. Let me bring myself back here. Let's go do this. You're not going to like this. Ah, my gosh. Okay. Let's do an example from your worksheet just to make sure you know how to set it up. I'm not going to solve it for you. The answers will be posted online, but you can go back. I just want to make sure you know how to set it up in the first place. Okay? So it says determine the energy released when 148 grams. So let's start with my Q equals, M equals, C equals, and delta T equals. Okay? So determine the energy released. So I don't know Q. When 148 grams of water, so I have the specific heat of water here on my paper, okay, and I can use either one. So for this one, I'm going to use, let's say, 4.184 joules over 1 gram times 1 degree Celsius. Okay, it's cooled from 95, so 95 is the second number, to 35. 35 is the first number. Okay, well that means when I do that, it's negative 60 degrees Celsius when I set that up. Okay, now let's set up our Q equals and set up my big grid here. With me? Stay out of the shadows here so you can see it. Okay, Q equals M, so M would be here. What was my M? It's 148 grams. Nothing goes on the bottom, 148 grams. My C, it goes in the middle, 4.184 joules. I had to label. Goes on the top. What goes on the bottom? 1 gram, 1 degree Celsius. Okay. Then I put my change in temperature over here, negative 60 degrees Celsius. Okay, now in order to solve, before I can do that, I have to get rid of the units. Change colors here. Okay, so let's look at the first unit. I have grams on the top left. Do I have grams anywhere else? Yep, right here. So I can get rid of grams, get rid of grams. I have joules on the top here. Do I have joules anywhere else? No, I don't, so I have to keep joules there. Degrees Celsius on the bottom, degrees Celsius on the top. Cross those out. So that means my answer for Q, whatever that number ends up being when I multiply 148 times 4.814 times negative 60, will be in joules. Okay? And I might as well, we're already here, let me grab a calculator. 148 times 4.184 times 60 negative equals 37,154, because I rounded, joules. Now, that should be a negative number, and why is it negative? Because I cooled down, okay? I lost heat, so that's why my answer is a negative number, okay? Feel free to check your answers online. Again, anytime we do these practice worksheets, I post the answers for you to see. Hope you got the information. If you have questions, email me, jkubuske@gocathedral.com, or feel free to visit the website, mrkubuske.wordpress.com. Have a great day. Stay warm.